and also the shader. And so I continued a little bit from yesterday, not too much, so not a lot was missed, but just had a thought of about some of the architectural things. And one of the more interesting things is this, yeah, rather complicated um, concept of vertex attributes, and especially the difference between OpenGL and DirectX. So whereas in OpenGL you are very much vertex buffer centric when you describe how a vertex attribute looks like. For example, if you have a shader that looks like this, I've changed it a little bit as you can see now. Um, so whereas yesterday we only had a position that would come in from the program, and we would transform it, so to say, and just push it onto the pixel shader. Now I also want to receive UV data, texture coordinates from the program, and pass this information on as a whole to the pixel shader. And so this means that what comes in is not only a position, but it's actually two pieces of data. So it's also a texture coordinate. So we have one vector 4 component for the position, and we have a vector 2 component for the texture. And this needs to be described. And the challenge here is that if you have something similar in OpenGL, this information is kind of bound to the vertex buffer where the data lives in. So you have the actual data in the buffer. So that would be the actual positions. Where do I have it? Here. The positions, and in that case also I already added the UV coordinates. So this is the actual data, and this would then live in a buffer. And then you would, in OpenGL, you would say, okay, this buffer is now associated with this kind of data layout, so to say. So it's buffer and the vertex attribute layout. But in OpenGL, in DirectX, this is different. The vertex attribute layout is there associated with a shader. And while it is not really complicated, it's not so easy then to have this common render interface where we want to have one single like list of API functions, but in the background we need to accommodate for both render backends. So this makes it a little bit more complicated, and because we really have this kind of mismatch where in one world we have to concentrate on the vertex buffer for the vertex attribute layout, and then on the other side we need to have the shader ready at the same place, and so it's a little bit um, not so nice. Let's put it that way. Um, okay, so but anyway, I had a little bit of thinking about this, and what I came up with is that I will define, let's call it a common vertex attribute description format, which is trying to bridge the gap between both worlds, which is what you normally try to do when you write such an API. And yeah, I called it just vertex attribute descriptions, and it has, in fact, a mixture of information that either one or the other backend will need. So the semantic name, for example, this is actually needed only by DirectX 11. But I think it doesn't really harm if the user uh, provides it. I think it can even make the code a little bit more clear, because I actually kind of like this idea that DirectX has here. And what is a semantic? The semantic is this thing. So this is a semantic, this, and this is also written here. Um, so it really tells, yeah, which attribute is linked to which kind of duty within the shader. So every attribute has a certain semantic, And whereas in OpenShell, you don't give it explicitly like that. In DirectX, you do. So in OpenShell, you would say, okay, I have a position, a UV, and a normal. So these come in, but it's still not clear for the GPU what the actual semantic is. So the semantic is handled there differently. In OpenShell, there is this kind of magic constants where you say, okay, the actual position semantic you have to assign to this variable. Then the GPU and the driver will know, okay, this is what he wants. This is the position here. Okay. So in OpenShell, it is done like this. So you assign it to a specific variable. Okay, that's fine. Just need to know it. There's no way around it. And in OpenShell, it's done a little bit differently, right? So it's really done with these kind of annotations per attribute, which is also okay. And also one thing that you might see here, so this is the texture coordinate typo here, I think. So this is what is called the semantic name here. And the 0 here is what is called technically the semantic index. Now, for now, to keep it more simple, I will skip the semantic index. And the semantic index is, as the name suggests, it's just like a counting number. So you can have, this depends a little bit on your graphics processor, on your GPU. Some have, whatever, 8 texture units, some have 16, 24, whatever. That depends a little bit on the price and the size of the GPU. But you could also say, okay, I do not only have one texture set, I also have a second one for whatever lighting, and you can call it texture light. And this would then go into another texture slot. So that's important. You cannot assign the same texture for the same slot. It would, in the best case, it would just overwrite the first one. So that's normally not what you want. But you can also not do that. You cannot say, okay, it's both are texture coordinates, because then the GPU would still not know which texture unit to put the stuff in. So in OpenShell, this is done like this. Sorry, DirectX, this is done like this with the semantic index. In OpenShell, works a little bit different. Again, we do not have semantics. So there you have other options where you say, okay, which slots the texture unit should be. But in the end, I mean, it's always the same GPU. So there also everything comes together, of course. And one program uses OpenShell, another one uses DirectX. In the end, it's the same GPU. They just have this finite set of functionality. And one more thing, if I'm not mistaken, I mean, I've researched it before. So if you write text chord or text chord 0, that's essentially the same. So if you do not give a semantic, DirectX will assume it is index 0. So that's fine. But as I said, in our engine here, for now at least, I will just skip it. And the consequence is that the vertex attribute format just has a semantic name. That's all. Because this must be given, but we will just set the index always to 0. So for now, we will just have one texture set, and that's it. Nothing more. The attribute location, I mean, that's also important. So for example, that's also true for OpenGL. So here it's even called location. I think that's what actually inspired me to use this name. So if we have a location 0, 1, and 2, this must match then with this vertex attribute description, because you must imagine it like this. So we send a stream of data to the GPU, and the GPU must know where which piece is. And you can split this information, in that case, into 3 different vertex buffers. So then the GPU would fetch the positions from one vertex buffer, the UVs from another and the normals from also another one, and you would just fill in the data into the different vertex buffers. This is normally slightly less performant, so what the GPU normally, from what I've read, prefers is to have everything in one buffer and just each piece of data, each attribute is following the other. So in memory, this would look like we have 3 pieces of vertex data, okay? And then we just have 2 pieces of UV data. And then again, we have 3 pieces of normal data, okay? But still we need to tell the GPU, okay, this is location 0, this is location 1, this is location 2. And we do this, yeah, with this location attribute. So, okay. Yeah, let's continue. What else do we have here? Let's have a look. Let's have a quick look at that, because that's the most important thing for the next half an hour probably. We deal with that. Yeah, the number of components. So this is it a single float, for example, or a rel2, like for UVs, reg3 for positions, normals, and stuff like that. Okay. The data type is necessary because this also makes a difference for the GPU. Is this an integer data? Is it a float? Obviously, they are differently represented in memory. So we need to tell it here, and therefore I introduced this data type, which is really just all kinds of data types that you might encounter in daily programming life. And so we will ask the user to describe which kind of data type it is. And then for both worlds, we are able then to translate into a specific OpenGL data type, because they look a little bit different. That's the problem. And for DirectX, they also look different. So this is why we have here the neutral representation, and then we will translate it into the specific ones. The stride, so this is now really important as well. The stride is actually giving the size of one logical vertex. And now again, we go back to this discussion where we said, okay, do we have actually all the data that make up one vertex, right? Is it tightly packed, one after the other? Or is one vertex just, so do we have, so this is the size of one vertex per buffer. And if we have it tightly packed, this means the size is the size of this one plus the size of the UVs plus the size of the normals. So then this would be the stride, right? So the size of all these 3, this would be the stride if it's tightly packed. But if we have it in 3 different buffers, then the stride in the first buffer is just the size of this position. And in the second buffer, it would just be the size of one of these vector 2 component. So this is why we have to be a little bit careful. And the next attribute just directly plays into that, because it makes sense to say, okay, if the stride describes how big one logical vertex is, then the offset is also very important per attribute. So the stride also essentially tells how many bytes do you have to walk until the next vertex begins, because that's also really important for the GPU to know, because this is like the size in which it can fetch the data. And the offset per attribute, because here we are describing one single attribute, you have to keep that in mind. So if we describe, for example, the attribute, let's go back here. If we describe the attribute UV, for example, then and then they are all tightly packed. That means the stride when the next vertex begins is still the size of all of these three together as a sum, but within this one vertex little data stream, the offset of UV is essentially the size of the position, right? Because if the position takes 1, 2, 3 floats, because it is a vertex, and then the UV starts, where does it start? It does obviously not start at position 0, right? It does not start here. It also doesn't start at position 2, it doesn't start at position 3, but it starts at position 4. Technically, it's index 3 because this is 0 based, so this would be index 0, 1, 2, so it will start at index 3. Okay. And this is what the offset is called. And the same for the normal, because the normal now, where does the normal start? The normal, so first comes the position, then comes the UV, and then comes the normal. So the normal starts exactly here, right? So this would be index 0, 1, 2, 3, 4. Okay? So it would start at index 4. Okay? 0, 1, 2, 3. 0, 1, 2, 3, 4. Oh, sorry. Yeah. Okay, good. Yeah, I mean that's probably all the explanation for this. And now, yeah, I'm just about to really implement this. I started a little bit, but I'm just really in the middle of it. So I think enough to follow along still. So what we're doing, so if you remember from last stream that we had this, it was called associate vertex attribute. So I renamed it a little bit. It's now describe vertex attributes. And yesterday it was just one single attribute because that was hard coded. We just wanted to make this work. Today, actually, the more realistic setup is to allow the user here, because this main is really like, so this would actually be our game. And in a little bit of time, we will write a small game with the engine to prove that it actually works. But for now, we still need to give the game, can also call it the client, the option to describe all kinds of attributes, right? Because the game should be free, of course, to have all kinds of shaders, all kinds of materials. One material and one shader will have one attribute, another one will have two, another one will have three, another one will have five, another one will have whatever. And the five, and you can have two shaders with 5 attributes, but they are different. One has 3 different texture units, one has a normal map, one not, and so on. So we need to be able to give to the client, which is normally a game or any other graphical application, in fact, the option to describe all the attributes that we need, that the game needs. Okay, so this is why we need to pass in a list, a vector of these attribute descriptions. And so the game now needs to describe exactly which kind of data it has here. So in our case, what we need to do, because we want to use this this shader here, I will just leave that. So let's probably move that down. So what I did, another change is, yesterday we just returned directly here from this main function of the vertex shader, we just returned a float 4, which is a vector 4. And we said the position, the semantic of this output here of this function is actual the position for this vertex. Now it's a little bit different. We cannot say that here. We cannot say that this is a semantic of position here, because we are not just returning a position. We are returning this structure, and this structure consists of these two attributes, position and texture. Probably call it UV. I like it more. So what comes in is two attributes, and what comes out. So this is essentially where we describe which kind of data we want. So this is not to be confused. So this does not come in here as a structure, but here we say this is in our vertex shader. As the input, we want two attributes. One is the position, one has the semantic of a position, and that's what we will need to describe. This is this thing. And one would be the UV coordinates, and it is texture coordinate 0. The output that is described here, so this is the thing that we return here, also has a position, but if you have paid attention, you might have seen, okay, but it's not called position, but it's called SV position. So the difference is that the outgoing position, we need to tell the GPU again, hey, this is not just any position, because the input you could have whatever 4 position values and you just do some calculations, whatever you want. Maybe you need this for a specific algorithm, but outgoing for the GPU, like relevant is only 1 position, because this is how it will do the projection calculation, all these kind of things. And we will come to this later anyway. But so this tells it, okay, this is the outgoing position here. And this is part of this outgoing structure. And here, as you can see now, this is a very simple assignment only. So the position that comes in will be assigned to the outgoing position. So currently, we are not doing any manipulation here. This will change because when we have a camera system and when we have a few matrix and projection and all these kind of nice things, then we will do some calculations here. But for now, simple setup, we just pass it through. The same for the UVs. You could now, for example, here implement some manipulation of the UV coordinates. We could scale it, we could put it upside down, we could put a sine function to it, a cosine function to it, so we could have nice wave effects, whatever. This is one of the places where we could do that. For now, we don't. We just pass it through. It's just simple as that. This is also more or less a pass-through shader. Okay, and then when the output structure is filled out, we just return it. Okay, and return in that case means it will be passed on to the pixel shader. So let's maybe now have a quick look at the pixel shader, how that looks like. Because now you will see it's actually, I did not even change it, right? So we can do that actually immediately. Might make sense. So now how would such a pixel shader now look like that actually needs to work with the data from the vertex shader? I mean, let's think it through. If, and maybe we would just move that out up here because I think it's easier than to follow. So now, logically thinking, what you can keep is the notion that float 4 will be returned from the pixel shader. That makes sense. Float 4 is like a vector of 4 components, and that makes sense for a color because the pixel shader's real goal is to deliver the color, right, of a specific pixel. It is called for every pixel, or fragment, how it's called, and it has to provide the final color. And we tell it, hey, that this is the actual color. It's a little bit of a strange name. It's called SV target, but this is the code name for I'm providing the color, whereas here we provided the position. In the pixel shader, we provide the color. So that's fine. I mean, we can keep that. That will not change, right? The difference will be now that the color in our old version was just a pure yellow, hard-coded, always. And in the future, what we want now, today, hopefully in the next 1.5 hours, is to have the contents of the texture, okay? And to do that, we need to sample the contents of a texture. And so what we need to do for sampling the contents is we need to apply the UV coordinates, right? Because this tells the GPU from where in the for a given vertex, for a given pixel, which part of the image of the texture do we want to take here. And so we need 2 things. We need to be aware of those UVs, and we need to have some kind of access to the actual texture, right? Because we need to now tell the GPU, okay, look, this is the texture, this is my UV coordinates, sample colors from there, right? And this is my output color. So we need two things. We need somehow a texture, call it texture, and we will also need, this is a little bit, yeah, it's a strange, but it's maybe not so easy to understand. It's called a sampler state. And I just call it sampler here because I think that actually makes it nicer, because you can imagine there are different ways how you can access data from from a from an image, from a texture, especially if you are imagining you are living in different resolutions. So, for example, you have a very small texture. Let's say it's a 64 by 64 pixel texture, whatever, a small logo, whatever. And for some reason, in your game, the area where you display, let's say, a rectangle with this texture is very, very big. It's whatever, it's probably it's a 1920 by 1080 screen, and for whatever reason you just blew it up, and this is the texture that you want to show, but that means that it would be really blown up. And now it's a difference of how do you interpret all the pixels, because what it means is that these pixels within the texture, a lot of them will show up in different places, because you only have 64 pixels in the source texture, but you need, for example, 1920 in the width of the target on the screen. So how do you stretch this? So which you take the first pixel of your, so many, or let's put it in other words, so many pixels on the screen would actually like point to the same pixel on the texture. And by the way, we call this a texel. So a pixel in a texture is not a pixel, it's a texel. So how is this texel then translated? And this is what the sampler does. And because you can tell in the sampler, okay, just if the first pixel is red and the second pixel is blue, and we need the first pixel 10 times and the second pixel also 10 times, just have a hard edge, they put 10 times red and then put 10 times blue, and that's it. There is no interpolation or anything. But you might also say, okay, that's not what I want, because that would look very sharp. It will have this pixel style look, which you might want. And then you can tell it in the sampler, or you might not want. And then you can tell it, okay, no, but actually do some kind of intermediary interpolation there. And if 10 parts are red and 10 texels are blue, maybe you just make a mixture, and I think that's would be some kind of cyan or whatever pink. And I actually want you to mix this a little bit together. And the closer they are differently mixed, stuff like that. So this all goes into the sampler. So you need the texture and the sampler. So the texture is the data, the image, and the sampler is like the method, the methodology, the way how to access this data. And you can play around with those different sampler settings, and yeah, it's quite nice. So the way this then works is actually rather simple. You just use then this texture, and then you just say sample, and you give it the sampler as the first argument, and you need the UV coordinates, but this is the last missing piece. Where do we get the UVs? So what we could do is, actually, let's think it through. So first, I will just try to somehow make it a little bit visual here. So let's say this is the pipeline here. So first comes the vertex shader. So here comes the raw vertex data. Comes in. It hits the vertex shader. and then it hits the pixel shader. It's a little bit simplified. You can have other shader stages in between, but for now, let's keep it like that, and then it goes actually into what we call the frame buffer, which will ultimately end up on the screen. So if we say that the vertex shader is run first and then the pixel shader logically, wouldn't it be nice to say, well, if this thing here returns something like that, maybe we just use that as the input here. I mean, that would be very logic. So we do not get nothing, but we do get a struct of v output, right? And we just call it pixel shader input. That's just the name of the parameter here. You could also call it output, but that would maybe be a little bit misleading. And now from this pixel shader input variable that we have now access to, we can just say, give me the UV, because that's what we want here. And we will return the color that we get. So this will reach out into the texture, give us the color, and then return. This will too. We can maybe make it like this. Okay. So I think what we also need to do now, we need to duplicate this because this is in separate files, so to say. It's a separate shader. I think we will need to also name the struct the second time here. Otherwise, I think it would know it. So there is also a way that you can have everything in one file, but for now, I have it in two. Okay, that should be it. I think from the side of the pixel shader, I think we're fine. I think we're good. We will see later anyway. But next thing is we need to still feed this data in the correct way, and we need to describe which attributes you actually use. But I think shader-wise, we should be fine unless I made a typo or something, but we will find out soon. Yeah, that looks good. Okay, let's continue. So we have these vertex attributes now, and so the way they look like is, maybe I will just copy that over because that makes it a little bit easier to fill it out. So the first thing is a semantic name. So the first semantic name that we have is called position, if you remember. The next thing is the attribute location. So this was 0. Then we have the number of components. This is 3 because that's a position. It's X, Y, and Z. The data type is a float. The stride is not 0 because the whole vertex will now be essentially 1, 2, 3, 4, 5 floats, right? So the stride would be size of one float times 5. If I'm not mistaken. I will just have a quick look. I think, yeah, I think that is correct. And the offset is 0 in this case, right? So here we have the text code 0. This is the semantic name. The attribute location is actually again 0 now, because it will actually be in the same, will just come from one buffer. Okay, we have two components because it's UVs. It's again a float. The stride must be again this. But the offset now is actually the size of one float times 3. Why is that? This is because we need the size of the position, and the position is X, Y, Z. Each one is a float. So we have the size of one float times 3. And then we have this the offset in bytes. This is then where the GPU can search for the texture coordinate data. Okay, I think that's doesn't look too bad. We will see soon. So now we have these vertex attributes. We pass it in, and in addition, we also pass in the vertex buffer where all the data will live, and also the shader program and also the vertex array. We need all these kind of information to really accommodate both worlds, DirectX and OpenGL, and because this is essentially our abstract render interface function here, which then is implemented by both render backends. And in the case of now, we are in the DirectX world still, because I want to kind of now push this further. And in the case of DirectX 11, now we take this neutral attribute description and we must transform it into something that DirectX actually understands, because DirectX doesn't know about this kind of data. Doesn't make sense to it. It's not known. I cannot give it to the DirectX driver. Won't accept it. So what I need to do is, because the driver wants these kind of things, like these official D3, D11 input element descriptions. So I have to transform this now. So what I do is I go through all the attribute descriptions that the game sends me. And for each of them, I pull information out and I transform it into a Direct3D11 input element description. Okay, so this is a vector of this element, and by pushing back each of them, I essentially create the correct format, so to say. And now we can see this comes together now, because what this does expect, and we can have a peek here. You can just look it up. It needs a semantic name, it needs an index, a format, input slot, and so on and so forth. So let's have a look how we do this. We have the semantic name, so we pull this out from our vertex attribute description. This is just a semantic name. And as I said before, we do not use the concept of a semantic index now in a dynamic way. We just use whatever we have. Or that's wrong, we just give it always 0 for now. It would be probably not so bad or not so complicated to just add an index here, but I do not want to complicate it now. So now, as I said, we have this data type here, which is not conforming to what DirectX wants. So we have this small little helper function, which is just here, which takes this neutral type, and you give it also the number of components, because that makes a difference, because it can be a float. But if it has 3 components, it is a vector of 3 floats. If it has 2 components, it's a vector of 2 floats. But if it has only 1 component, it's just a single float, right? And especially in DirectX land, that's a difference. So based on these 2 informations, this is not fully implemented yet, but it's just handling the most frequent case, which is a float. So if you have a float, and if it has 3 components, we give back this kind of vector type, which is like R32, G32, B32. It's just 32 bits. So this is a 3 component vector, and each has 32 bits or 4 bytes. In case of 4 components, it has 4 floats, 2 floats, and 1 float. Okay. And for now, we just say, well, the standard case, the default case, is just a 3 component vector. Okay. This just handles the type, and then what DirectX calls the input slot, I translate this from our input attribute location. And we also have the offset here. This is important. So as you might see, or just continue, then I will say what I wanted to say. And this is just the input slot class. So this is just input per vertex data, because there is different kind of like granularities on how you can send your input data, but this is the most simple one for now. And this is the instance data step, right? So this is a little bit more advanced topic again. This is if you do instance rendering. So if you say actually the data from this one buffer, which might describe a tree. So all the vertex data is describing a nice little tree. I want to render this now for a forest 1,000,000 times. That's it, 10,000 times, however often you want. And this is very convenient. And you can then tell the GPU, okay, is my step rate, so 0 is actually not instance, but you could say the step rate is 1, or it's like how many, I think I'm actually not totally sure now how that would really work, but the most common way to use this is a step rate of 1, and you have, let's say, 1,000 instances, then it would just um, for every new instance it would just draw the data from this one buffer. And then obviously you would then also need to do some transformation, because otherwise each tree would be in the same place in the center of the world. That's not what we want. But we don't do that now. Very, very surely will not do it today. Anyway, but maybe in another day. Okay, so now we have the attribute description. That's nice. And we just create the input layout. So the input layout in DirectX World is just describing to the GPU, yeah, how does the input of the vertex shader look like, and you'd have to tell it how many of those layout descriptions do you have. So in our case, that would be 2. I will see. I will debug it soon. We will need to give it some reference to the binary of the vertex shader. This is a little bit complicated, but that's how it is. And also give it the size of the binary of the vertex shader. And this is just the receiving layout variable here. So this call will then put the final input layout into this variable. And what I do now, I remember it, I store it in this what I call a DirectX 11 vertex array. This is something virtual I just came up with, because a vertex array is a concept that doesn't really exist in in DirectX. It just, sorry. It really just exists in OpenGL. But so for the sake of the common interface, I had to reinvent the wheel a little bit and just kind of come up with a virtual vertex array in DirectX World. And it's really a container which stores all kinds of information, because I need it later when we're drawing. So here you see it's what I call buffer wrappers. This in turn is also something that is storing a little bit more than the actual DirectX buffer alone. It also stores the stride, which we talked about, and also stores the offset. And we have a list of this here for one vertex array. And we also normally have an index buffer. And this is the input layer that we just discussed one moment ago. So here this comes from. Okay, yeah, I mean, let's just see if this even compiles. I'm really not sure. Maybe it does. Hope it should. Yeah, I mean, at least it compiles. So now let's just quickly do some some debugging here. Let's probably remove this, and yeah, I mean, let's really start here. I think the rest is fine. And yeah, so here you can see I already prepared some texture loading, but yeah, we'll come to that a bit later. Let's just see if this really works, or if we have some kind of bad surprises here already. So, which I think we have, because we already have a null pointer here, as you can see here. And So there is something wrong here. Let's see what it says. Let's go over it and okay, there's an unexpected token texture. Okay, let's see. So this is in the pixel shader, which is here. And it's called texture. Okay, let me quickly check this. Check this out. Let's do some research. Okay, let's see. I mean, we have the maybe we'll see if this is actually at compile time or when we are setting it. Let's see. So I think structure-wise it should be okay. Should be okay. Oh, okay. Oh, it's the okay. Okay, texture is like a specific word, so we will just call it. We'll just call it image texture. I think that should be fine. Because it's a keyword in HLSL, it seems. At least that's what Google says. Let's try it again. I think it should work. I'm optimistic. No, does not work. Unexpected token sampler. Sampler probably the same, I guess. Yeah, then let's just call it sample state. I don't like the name state here, but maybe at least the texture problem was solved. Yeah, much better. So we survived this now. Pixel shader compiled. That's good. Now let's see. Let's jump into this and create. I suppose we have two of them. Yes, two layout descriptions. And the first one has a semantic name of nothing really. That doesn't really look good. Okay, I mean we have to look at that because this is not okay. And this I think also doesn't really doesn't really make sense. Okay. I mean they look identical really, which doesn't make sense because one should be this is the position, that's fine, it's the first one. The second one should only have two components. No, which it does not have. I mean it has an offset. This is okay. But some things did not really work. Okay, I mean that's okay. I guess we will just debug it once more and just go directly here. Maybe even there, and just don't need that. Okay, let's see. What do we have? So now let's really see if this is already wrong. So the first one that we have now is the position. It has three components, it's a float, and it has a stripe of 20 bytes, and the offset is 0, which looks correct. Which looks good. So the first problem that we already have now, let's just see, is that the layout description. Okay, yeah, I mean, it looks much better now for whatever reason. It doesn't really make sense. Yeah, I mean, that looks good now. So now the second VAD, what is it? Okay, I think you don't see this well. Let's do it here. So the VAD is called texture code. It's attribute location 0 as well because it's the same buffer. It's fine. Two components, stride 20, float, offset 12. Three floats with each 4 bytes 12. That looks fine. I mean, that's actually okay. So the funny thing is that now they are 0. I don't really understand why, but that is the case. How can it be? And they are actually totally the same now. Okay, no, let's just go back once. Let's, yeah. So, layout descriptions. Let's have a look at that. First one is already bad. Yeah, somehow this is just not working well. I mean, let's just do it in a different way. Let's just say we create a description, and this is a directory D11 input element description, and we give it all of this. And then we just push back the description. I mean, for whatever reason, this did not work so far. Let's try it again. I mean, I'm really not sure what's the problem here now. Maybe I need a reference somewhere. So the description itself looks okay. Now I push it back. Is it still okay or is it already broken? No, I mean it looks fine. Okay, let's see. Yeah, it should copy everything, right? I mean, why not? So the description again is fine. It is added, and again it's broken for whatever reason. So we need a pointer here. Is that really it? I'm confused. I don't fully understand why it does that. Okay, he's not happy. Okay. Ah, yeah. Now it's getting magic. Not too happy about that actually, but yeah, what can you do? Yeah, still looks nice. And it's already broken. I mean, it's already bad because you see, it's already wrong. And it's always the semantic name. I think I'm really confused. Why would that be the case? Why would that be the case? Could check, see. I will just quickly check. How could that be the case? Okay. Yeah, it seems that's what I thought. I think this is a problem. Mm, okay. Yeah. Okay. Okay, I think, yeah, okay. Yeah, we really need to save, it seems. Okay, other people do it like this. Yeah, so this is a problem because this is a temporary pointer. This goes out of scope, and this is also it's kind of the memory reuse. So this is where we see the second name overwriting the first one. So what we can do is, first of all, we don't need that. That's stupid anyway. We don't need to have a pointer here. But what we can have is a standard vector of strings, and we have our saved strings. So the first thing, because now this is it should be a stable thing, hopefully. The first thing we do now is we save it here. And then until we use it from here. Save strings, like from the end. And then we use this. I mean, I'm not, so maybe I was stupid anyway. I mean, if I say, no, 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 let's try it. I mean, I'm not sure if it really makes a difference, but let's see. And it seemed that was also a problem, but yeah, I mean, let's see. So how does it look like? The first one looks good, but that's nothing new. I mean, we know that already, that this works. So the saved strings, how do the saved strings look like? Are they okay? Yeah, they are okay. And oh no, that doesn't look good. Oh no, it's again. I mean, yeah, it's again corrupted. I mean, is it the back? What is the back? So it should be the last one, right? Once again. Oh, that's a pain. That's painful, but that's coding. A lot of the times, what can you do? I mean, what I'm wondering is, no, it's fine. So the back is, they look fine. They look nice. What's the problem? Yeah, that's okay. Yeah, it should be fine, right? So now the back is text chord 0. And the crazy thing is, it's already in the shit. It's already bad. So how can we do this in the most elegant way, or maybe not even elegant, just do it anyhow. Hmm. Um, hmm. I think the pointer is still a problem. Maybe it's the copying of the. Yeah, I had this with the window as well. Maybe that makes it more stable. Let's see. So, I mean, this is fine anyway. That was not the problem. Push it back. Yeah, I mean, this works anyway. Let's see now. Oh, I think, I think. So it is breaking when we do the, when we, so when you push this into the saved strings array, seems, hmm, let's see, maybe this is already a problem how we put this in here. I mean, this is this it? Maybe it's here. Hmm. Oh, I think No, I think that is fine because this is, this is actually nice. Why? Let's see. This comes in, it is actually, I mean, this should still live, right? So the attribute description should still be on the stack, very stable. Should not be a problem. I don't see any problem at all here. Why? Why would that be out of scope or something? I mean, it clearly is not. Hmm. Yeah, I mean, maybe we should really just split it up. We'll probably do it like this. So all these memory lifetimes do not interfere. So we'll just do that. And we will probably int counter equals 0. And then we will just do this. I think that's more stable. And the counter will just increment it every time. Yeah, we can also use a for loop, but I think we can do it like this. So the problem here is with the memory lifetimes essentially, and yeah, it's a little bit more complicated. So now it's still fine, I'm sure, but that's not the point. So the point is now it's still okay, and it's still okay, and the actual description now is like that, and this is now hopefully fine. Let's look at how the descriptions finally look. Yeah, I think it's totally correct, but it's better. So we have the position, we have RGB, that's fine, 0, 0. And I think that's fine. But the second one, the text code 0 is now fine. Okay, that did it, but this is not okay. The offset is okay, but this is not okay. The format is not okay. So something is off here. We need to check this. We need to check this for the UV coordinates because it works with because it works with the vertex with the position attribute, but it does not work with the UV attribute. So the first one we can skip because this is the position, we don't care. Sorry, too late. It was too late. I need to put it here. I need to put it here. And so the first one we skip, and now the second I go into the dungeon. I go into, oh my god. This is where I wanted to go into. Oh, number of components. Okay, yeah, because I'm stupid. Yeah, I saw it. Okay, sorry, because yeah, so the default is free if you don't give it, but I need to give it because this is the VAD number of components. Now it should work. Now it should work. So I think you can skip it actually. Just have a look at the end result, and the end result is much better. You see, so now we have position and it's an RGB because it's three components. and here we have text chord, and it's RG because it's two components. Voila, that's good. Okay, wow, that was heavy, not fun. Okay, so that did not work. That did not work. So the result is bad. So then we will just do this differently. Oops, we say if failed. Now comes the interesting part. So if the result failed, I want to write some more, and I also will turn on my directs, my debug view. Sorry. So create device. I think we can do that. I learned it yesterday. There is this macro here. And I think we can probably use this here. Because this is no, it's not present, but it is. Doesn't really matter. Yeah, let's see. Let's see if we see something here. Hope we do. I sure hope we do. So I mean, is this okay? Yeah, I mean the blob is existing at least. It's not. That's fine. Yeah, it's not looking too bad. So now let's see. Wrong parameter. Creation of input layout failed. Wrong parameter. How nice is that? Okay. Wrong parameter. What the hell? No, not here. Sorry. Let's go here. Wrong parameter. Okay. Let's Google that. Which parameter could be wrong? I would say they are all very nice. No, it's called text chord 0. And we also call it text chord 0, which is fine. So that's okay. Maybe, oh no, I think it is actually, yeah, I think I need to then, yeah, I think I still need to do it like this because it would concatenate the 0 anyway, right? So let's do that. Let's do that. Yeah, result is 0. Yeah, we're good. Wow, now we have an input layout. Okay, kind of milestone reach. We have an input layout. Now, short introduction. I made a quick load image function, and this uses actually a library, as you will see. I use this STBI load library. The library is called STBI image. And the nice thing about it is just one single header. And yeah, it's free. It has a good license, and you can just download it from GitHub. And it's really a very lightweight library, so that's very nice. And yeah, you see it's just one call. Just say SDBI load, name of the file. Then you give it some slots where you want to store the width and the height, and it will tell you how many image channels it has, and we say, yeah, we expect 4. So for monochrome images, we will probably change that in the future, but for now, that's good. That's fine. So we can run that, and then the first thing we see is if the width and the height are good values. In that case, it is. It's just 1024 by 1024. That's nice, and that's exactly how the image looks like. I can even show the image. The image is here. Yeah, it's just whatever. I just took one of the simple low poly textures of a figure I made in Blender, and it's a 1024 by 1024 PNG. So that looks correct. And so this is the actual raw image. So now we have the pixels in memory here. Here they are. And now we will actually create the DirectX 11 texture. And this is done with this small function I did. First we check, do we actually have pixels? Because if not, we will just, for now, explode. And then we just fill out these typical informational structures. We will assign the pixels to the memory. We will have the memory pitch is the width of the texture of the image times 4, because we have red, green, blue, and alpha channel. And sysmem slice pitch, I have no idea what it is. I just set it to 0. And now we create the texture, and we have hopefully a good result, and we have. And now there's a special thing you cannot really use for whatever reason. I don't really know. You cannot bind actually the texture itself. What you bind technically is what they call the shader resource view. And this is linked to this texture, and then I think that's for sure for efficiency reasons. So this is what we do. We create one of these, we associate it with the texture that we just created before, and it succeeded. We survived the assert here, and now we just store everything in our abstract texture object, and the texture is something like that. I called it DirectX 11 texture, and it actually is a combination of all these things. So it's the texture itself, it's the shader resource view, and for future use, I also already prepared these kind of additional information. So these both are all necessary when you do off-screen rendering. For example, if you do screen space post-process effects, you need to render into a separate frame buffer. So you then would not render directly onto the screen, but you first render into a texture essentially, and then you do all kind of effects with this texture, and then you present the final piece to the screen. But this is where these two things are necessary, because this is essentially like the color frame buffer part, and this is like the def and stencil frame buffer part. Okay, but going back, we just memorize it, we store it here, and we have it here. We don't use it yet, but we have it here. So, I mean, I can let it run. I think we will see probably nothing. I can show you what we see. Is this the test game? No, that's not. Sorry. No, that's actually not the test game. Doesn't make sense. Oh, yeah, I mean, maybe it doesn't make sense. No, it's my window here. It's my window. Why does it look so stupid? That's interesting. Because that's not how it looks for me. That's not how it looks for me. Okay, this is an issue I need to solve because otherwise people in the audience cannot follow what we see. I think that worked yesterday, right? So why wouldn't that work now? Let's try to do that. It doesn't make a difference. Ah, yeah. Okay. Hey, look now. This is how it looks like. So we have the green background and we have a black rectangle. So that's not totally wrong. So the first thing we do need to check is, I mean, I'm not sure about the triangle now here, but anyway, we don't even upload the texture to the shader anyway. So we need to do that first. Okay, let's try that. Um, so now we will bind the texture, and we need the texture. And yeah, the idea is now, because the texture is just here, that doesn't make sense, right? So we will have to put it into the game state so we can pass it around. This is just our one single texture handle for now. And no, I want it here. And now I can hopefully use it, because now I can say, look, game state, graphics, texture handle. And I think, oh yeah, and I need to tell it the slot here. In that case, it's 0. And again, this is also mainly because we have this difference between OpenGL and DirectX. Both need to know the slot, but in slightly different ways. Yeah, I mean, let's just see. Let's debug this first, and maybe it works right out of the gate, which I couldn't even imagine. Maybe it does. Okay, this we already know it works, so that's fine. I think we don't need to do that. So bind the texture, hopefully. So the way this works is that we just, first of all, we grab our abstract texture thing here. So we have this here now. And you see technically it has the IAD3D11 texture to D object set to something, which I think is fine. And it also has this famous shader resource view set to something, which is also, I think, good. And now it's actually quite a nice functionality on the DirectX 11 context. We just say set shader resources into slot 0, and then the texture resource view, the shader resource view of the texture. And you can actually set more than one at once. So you have to tell it how many you set. And we do this here. And the samplers are set separately. So, and yeah, where does the sample state come from? I can show you guys that. So this is the default sampler state, and it is just created here in the init function. I just set it here. I just say, well, this is my default sampler state. Why it's a default? Because it's just giving some good default values, essentially. Just saying, well, you can just wrap the texture around. it's a linear filter, so that's what I mentioned before. So it's so this is not probably what you want for a pixel art style, but this is like where it tries to interpolate across the whole image. And this is normally a good starting point for something that looks reasonable. So this is where this comes from. So we set this here, and the problem here is that this is just a void function, so I cannot even check if this really worked or not. It's just we have to assume it did. So yeah, let's render and let's see how it looks like. And yeah, I mean it doesn't look that bad actually. I can, as you see, I mean it's something. Now we see something. So the problem is now maybe that somehow we have lost the fact that this is a quad. And it should be a quad, but it is a triangle only. So it's not that good still. Probably will have a look at render doc for that matter. And let's launch the thing. And let's have a look. And render doc, where are you? Here you are. Let's put you here, and here we go. Fine. Okay. What do we have? We have one color pass. We draw actually 6 vertices, so that's a quad. That's fine. It's fine. And we have okay. That's what it looks like. It seems like the mesh data is somehow mixed up. Okay, let's look into the mesh. Wow, that's weird. That doesn't look good. That's weird. So the first one is 05050. Bottom left. Oh, I see. I think the problem is now we have, so it is a problem. What I can see is it is a problem with the vertex attributes. So now they are not correct. They're not correct. And that's very probably an issue with the vertex buffer now. Let's see. Yeah, I think, yeah, look at that. This is the problem. So the free is correct as long as I only had the positions, right? But now it's not free, but it's 5. So this is one vertex, this is one vertex, and this is the problem now. Because the stride is actually given in DirectX 11 land, it is given here. And for this buffer, we need to tell it the right stride, and the stride should be 5 now. And maybe it works now, just out of the box. Let's see. Yeah, here we go. I mean, it's a it's not a nice texture, but we can actually probably just do a more nice texture. But yeah, I mean, it works. That's fine. That's really good. Okay, cool. So I think the next very important and big thing is to actually create something like a virtual camera, because when we have that, we can do zooms and we can do movement with the camera. And when we can do a camera, that means, and if you can transfer the camera into the shader, then this means that we technically will also be able to do other transformations in the shader, and this is necessary so that we have different game objects that just move and rotate and do whatever. Okay, so let's just see how far we come. We have half an hour left, and yeah, just do our best and at least prepare some things. I think we can start with the shader, because in the shader is where the music plays. And I have already prepared this from my old project here. As you can see, I'm just trying to check this. So what we can do is, or what we need to do is tell the shader, hey, look, I want to, okay, no, I need to fix this now. What we actually want to do is, I need some matrices here. I need to do some transformations. And what we need is normally the big three. So we need the model to world matrix. We need the view matrix. This is what the camera sees. So it transforms like from the point of view of the camera to the screen, and the projection. So this is like projecting the image that the camera sees through its lens. Like this is really projecting it onto the screen. But the view matrix is necessary to actually have the correct objects in the viewpoint or in the viewport of the actual camera. So what we need is some way to have three matrices here. One we will call the world matrix. One we will call the view matrix. And one we will call the projection matrix. And maybe let's make it a little bit nicer. Just a little bit. And what you can actually do now, and what I normally did, is that you can put this into a so-called constant buffer. And these constant buffers, you can fill with data from the CPU, from our client program, from our game, every frame. We'll not do this per vertex, but we'll just do it per frame. And no, not per frame, but per object. And an object can have many vertices. So you have different granularities. You have per vertex, that's essentially the most granular one. You have per object or per mesh. That's already not so often. And then you have per frame. And here in this case, this will be per object, because every object might be rendered at a different position. So we need a different world matrix at least. We could argue that maybe we could have a different buffer for view matrix and projection matrix, because these two essentially form the camera. And this is the per object transformation. This decides where in the world is it. So this is movement, this is rotation, and also the scale. Okay. So we could technically put this into two different buffers, which could make sense, because one, we upload only once per frame. This is the camera, because we assume for now that the camera doesn't change per object, which it could in the future, but for now we could actually have a separate buffer for that. Let's do that. So this is what we call the camera buffer. Then we don't need that anymore. And this is per frame. And this we call object transform. And this is per object. Maybe we will just start with that and we will see if we can probably rotate the image or something like that. Maybe we can do that. Okay. So this is one thing. And now to actually, so if we want to have a rotation, translation or scale, we need to multiply the incoming position with the matrix, right? So how we do that is there is this command in HLSL, which is called mul for multiply. And first you put the actual vertex, and then you put the corresponding matrix. In our case, this is called the word matrix. And the first thing we will do now, because I'm really not totally sure about that now, is to let this compile the shade and see if the shader still compiles. I'm not totally sure now. Yeah, it did. I mean, we don't see anything now because the word matrix is not set anywhere. But and this is where the position is now completely off. But we will get there. But at least it compiled, so I think that's good. So what we can do now is we will need to somehow we will need to map a resource, I think. And yeah, I think what we need to do is, how did we do that here? So we had this, we call this bind texture, but we will just do it a little bit differently now. We will, how do we call it? So what we want to do is we want to update constant buffers, essentially. Let's probably just call it for that. I mean, I'm also trying to think in the back of my head what we will be doing with OpenGL, but maybe I will think about that later. We'll just do it now for DirectX and then care about that on another day, so that we just move forward. Because I think this concept is actually not that different. So OpenGL and DirectX are kind of similar in that regard, actually. So I think we can just call it upload constant buffer data. And we will just essentially give it some kind of data because we really don't know what it is. We need a size in bytes. Sorry, call it size t. Size in bytes, and we need what? I think yeah, we need a buffer for that, and that's fine. Yeah, I mean, I think that's probably it, right? Okay, we can just implement that because that's easy, and I have it still in one of my old projects. I can just move that over. Wow, what is he doing? Already? No. I mean, yeah, I mean, it's not that bad, actually. No. Hey, why? Why did you do it again? Do it again. Crazy. did he do? I mean, it wasn't that bad, I think. I'll just use my old stuff here. So I had something like a frame transform buffer, obviously. Like what I explained, this concept is that you want to optimize how often you send data over the bus, PCI Express bus to the graphics card, and you want to do it as little as possible, as few times as possible, obviously. Every transfer costs time, costs performance, costs frames. So it really makes sense that you are aware in your shader, hey, which kind of data is only going once per frame. Yeah, you send it once per frame and that's it. And even if you have then 1000 objects that are rendered, this data will not be transferred again. So this saves bandwidth. Which is per object and which is per vertex, right? So per vertex, this is not a context buffer, then it's a vertex attributes. That's what we dealt with before. And but you can also have context buffers per object. Okay. So here in my current project, this is called context. This is called the context. Oh. And yeah, this is how this was called, but I will just yeah. I mean, this is just in fact this simple line here. Yeah, let's say we also need the int 22t is the buffer slot, and we will use that. And the number of buffers now, it will always be one. I don't want more than that. And this frame transform buffer. Okay, and it is just a so we have, so first we need our buffer. Also the buffer is, so this is the buffer handle, and we now have the buffer is buffer handle buffer. So this is the real buffer. This is now, so we map the data so that we are allowed to write to it, right? So uploading means get it pointed to the actual data. So what the driver will do, it will go to the GPU and provide you some pointer to some memory on the CPU, I believe. I think it's then transferred by the driver actually, but it gives you some point in the memory where it says, okay, yeah, then upload the data there, and then I will take care of actually transferring it to where it will end up on the GPU. But for you, it's like this is uploading. Buffer, that's fine. What is the size of? Does the size of this mean here? Ah, yeah, okay. Ah, yes, okay. And we need the size in bytes. I mean, that's it. Just use that size in bytes. And no, this is whatever map this. Yeah, this is the data. And makes sense. Because I think this is already good enough. We need again the buffer here. So we unmap it, we give it free, we release it. And then we just Yeah, it's always nice. We will just call this. So we will just do an iDirect3D11 buffers exactly in Nuit. That's what I want, because technically we need to tell him it's an array. Okay. And this. Oh no, sorry. I mean, we already give it a buffer handle anyway. So, oh no, yeah, I'm stupid. This is buffer map. Ah, okay, we don't have a buffer map. Okay, no, but let's say we have constant buffer map, and we will use the buffer handle ID. So now we need to create actually something. So we don't create a vertex buffer, we need to create a constant buffer. How nice. Graphics handles. Yeah, I guess that should be fine. Let's see. Do that. So I will just check how I did it with the frame buffer last time around. No, I don't need the frame transform. I just need the size. Size is the size, and the important thing is this here actually, right? So yeah, and I think we will just do graphics handle, and then we will go into the constant buffer map, which I think does not exist, right? So static. Oops. Yeah, let's do it. Let's make it like that. Constant buffer map handle ID equals. Do we need to also create it? We need to also create it first, actually. Otherwise, it doesn't make sense. This is just called device. And this is. I think we will just. Just do that, and there goes the buffer. And it's fine. How did we do that? Yeah, no, that should be fine. Okay, yeah. I was just wondering if we have a dangling pointer there. I think it's fine. I think it's fine. Yeah, so we now need a DirectX 11 buffer wrapper. The buffer wrapper has a buffer, and I think the stride here is really the size actually. And then we have, come on, and the offset. Yeah, I think the offset is also not really, doesn't really matter. Why would that help? Yeah. It always likes this more. Okay, it's fine. And then we return the handle. because that should now work. So that should be it. Retrieve the buffer from the handle, okay? And yeah, so the first thing we need to do is to create something like that, because maybe we will enhance it. And we will create a struct. I will just call it the same because it makes it a little bit easier. And this will be a GLM matrix 4. This is the world matrix. Then we will now also create a constant buffer, and we will create our world matrix in a way that it is GLM rotation. Okay, I need to find the correct. I think it's this. So I need the import of GLM. I think, yeah, it's rotates. Yeah, 45 is actually nice. Yeah, I mean that's actually good, and around C. Yeah, so I want to rotate it so that we see it when we look at the screen. So now the data is GLM data point. Data pointer, how is this working? Update. Worldview protection. Yeah, let me quickly check. It's called a value pointer. So I think, so we need a way to actually upload the data. Oh, 5 minutes left only. We'll include this here. And I think what we do now is we call world matrix. And this is the size of this is then the size of a GLM mat4, right? Nothing more, nothing less. So now we have the constant buffer. So let's say graphics. Object, how do we call it? Object transfer buffer. Let's call it object transfer. So we need to create this. Yeah, that makes sense. I like it. And let's see if that works. Let's see if that works actually. Before we continue. In the end spirit. Yeah, anyway, if someone has questions, please just ask. Anytime. I hope I can answer them. I will try. So sorry, I didn't really have my breakpoints ready. So now here we go. Okay. Dynamic because we'll update it every frame, every object in fact. Bind the constant buffer. Yeah, we want to write from the CPU directly. No, no flags. Let's see. Did it fail? No, that's good. Graphics handle. Restore everything. And the size 64 bytes makes sense. 16 times 4. 4 columns, 4 floats. Handle. Yeah. And I think we already seen nothing is showing up now, but we're close now. So now what we would do now is 3 minutes left. Yeah, we'll call upload constant buffer data. That's it. Yeah. That's it. I mean, actually, maybe I wouldn't even need the data here, but I will leave it for now. Let's write to do. We might not need the data here when doing buffer creation, just when uploading. I'll probably fix this later in the evening or something. And then we say upload constant buffer data. But we don't say it here because we do this on the occasion when we render. And yeah, so we want the world matrix now again here, but yeah, that's fine. I mean, we'll just copy it for now. That's a bit dirty now, but it's just for the sake of doing it. So this is actually now again the data. Actually, the same thing. Doesn't really make sense. Yeah, no, it should be fine. So we do GLM value pointer of the world matrix. Oh, size of GLM. Yeah, that's it. Let's see if this works. I mean, if this does not break, it could. Oh no. Oh, okay. Ah, yeah. I think no. What is the upload constant buffer? Nice. Something is off. Ah, yes. Buffer slot. There we go. Okay, last call. I think we have seen that. We've seen that. We have not seen that. At least we have a buffer. Yeah, it's nice. And look at that. I mean, what a wonderful point to stop. Okay, so now we did the translation, or in that case, we did the transformation, which is just a rotation, and it is 45 degrees. That's a wonderful point to stop, and I have to stop anyway. But as always, thank you very much for joining in, and see you next time. Due to holiday, that will be, I think, on Wednesday or Thursday. Just check it out in the calendar. And have a good time until then. And next time we will continue there and we'll move into gameplay territory probably soon, because now we can do already some things and that will be cool. Have a good time.